Okay, for number 28 example, I thought of another way to use the screencast program and show you a video of my solution. We'll see how this works. So the next example is number 28 from chapter 4. We're given two forces, F1 and F2, shown in the figures, and we're looking down on this object. These two forces are acting on an 18.5 kilogram object on a frictionless tabletop. So we're ignoring two forces. If we're looking down on the tabletop, there should be pull of gravity straight down into the page or down into the tabletop, and then there should be a support force of the table straight up out of the page or straight up out of the table. But assuming this puck or whatever it is stays on the table, those two forces should be in balance. And so we'll sort of ignore them for now. We also have not yet developed notation for vectors that point into or out of a page. We actually, we might do that when we talk about rotational motion, but you won't really use it until you start talking about electricity and magnetism and induction. Okay, so ignoring those up out of the page and into the page forces, F1 and F2 in part A will cause a net force because they are not in balance and they're at right angles to each other. So we need to find the net force on the object and its acceleration. F1 is 10.2 newtons long and F2 is 16.0 newtons long. These two forces can be added using the tip-to-tail method or using the parallelogram rule method, where the two forces form adjacent sides of a parallelogram, in this case of a rectangle. The sum of the two forces is the diagonal of that rectangle. This is the same as tip-to-tail, so here's F1, and then we would place F2 so that it begins at the end of F1 and comes down here. And again, the resultant will be from the start of F1 to the end of F2. So either way you do it, you get the same resultant vector. And either way you do it, this resultant vector is the hypotenuse of a right triangle. I'll try to highlight that right triangle, smearing the ink. There's your right triangle. So the right triangle has sides of F2, 16. I'm going to drop the units just to make this a little bit less messy. And 10.2. So the length of the resultant, or the magnitude of the resultant, is equal to the square root of 16 squared plus 10.2 squared. And, I wonder if I can put this where you can see it. There you go. I don't know, this is going to end up getting a little crowded, but 16 squared plus 10.2 squared, and then I take the square root. So I have a resultant magnitude of 18.97. More units than we need, or more sig figs than we need, but that's fine. And then we need to know the direction as well because it's a vector. So let's look at this angle right here. We'll call that theta. So if I define theta as this angle, then the inverse tangent of theta, or rather, theta, hang on a minute, let me back that up. Tangent of theta is equal to opposite over adjacent, so tangent of theta is 10.2 divided by 16, and so theta is the inverse tangent of 10.2 divided by 16. You will want to note whether you're in radians or degrees. For now, we prefer to be in degrees most of the time, all of the time. Let's see, and then I want to, now, my calculator is not the best for trig because of that weird little list you have to go through. So 32.5 degrees. For the angle, I'm defining from the negative y-axis counterclockwise, no, with clockwise, negative y-axis clockwise. You could define it as the angle from the negative x-axis. Counterclockwise, it doesn't really matter, as long as you note which angle you're talking about. So we're still not quite done because what we've found here is the magnitude and angle of the net force, but that's not actually answering the question yet. We want to find the net force on the object and its acceleration. So now we need to apply Newton's second law, where acceleration is equal to net force divided by mass. So I can say the magnitude of the acceleration, at least, is equal to the net force, which I now know is 18.97 newtons, and I divide by the mass, which was given of 18.5 kilograms. So the acceleration is pretty close to 1. Let's call it 1.03. And our units are meters per second squared, because a newton itself is a kilogram times meter per second squared, and we're dividing by kilograms. As we mentioned before, the direction of acceleration is the same as the direction of the net force. So we can say that the acceleration is 1.03 meters per second squared at 32.5 degrees from the negative y-axis, or however you want to call it, negative 32, or rather 32.5 degrees clockwise from the negative y-axis, if we're going to be really super clear about it. All right, so now we're going to look at part B. This is rather a little bit more complicated. So 28, part B. Now we have F1 and F2 not at right angles to each other. So here's x-axis and here's y-axis. F2 now points directly along the y-axis, and F2 is our 16 Newton vector. But F1 is 120 degrees clockwise. F1 is slightly smaller. F1, which was 10.2 newtons, is 120 degrees clockwise from F2. I don't love that. I would prefer to define it from the x-axis. So I'm going to say this angle, 120 minus 90, is 30 degrees. So I can't proceed with adding these vectors, at least not easily, without decomposing F1 into its x and y components. So I zoom in, I focus in on F1. Here's my x-axis. I know that F1, 10.2 newtons, is 30 degrees below the x-axis. I'm trying to find the component of F1 that lays along the x-axis. So this is the amount of force that lays in the x direction, and it's as if I shone a light on 10.2 newtons, and I'm looking at just the shadow that falls in this direction. That is the x component of F1. I can label it F1x. Same story, other direction, F1y. And now I've created my right triangle. X and y are perpendicular to each other. I know the hypotenuse length, and I know angle 30 here. So I can say that the sine of 30 degrees is equal to opposite to 30, so F1y, divided by hypotenuse 10.2 newtons. F1y is therefore 10.2 newtons times sine of 30. And now is when you really need to check that you are in degrees. If the angle here is measured in degrees and you try to calculate sine of 30 degrees, but you're in radians, you'll have errors. I'm calculating this value right now. So 5.1 newtons. And then F1x will be 10.2 newtons times cosine of 30 degrees. Using the same reasoning here, except cosine of 30 is adjacent over hypotenuse, and then rearranging. And this is 8.833 newtons. So I've got my two components, and I'm reaching my recording limit. So I'll pause here and restart the recording.